Okay, okay, good afternoon. Right. So today, so far, we have done about 70% of the topic one. Last time we discussed the use of ICT in different areas, and also we discuss so we have done these things now. Okay, so these things are done. So you can see that we are gradually finishing because we want to start something, finish something. Okay. And also we discuss the social and economical aspect of ICT also. So there we have small topic that is legal and ethical aspects of ICT. So ICT related legal aspects, ICT related ethical aspects. So that we will be doing next time. Right. So then topic one is over actually. Okay, topic one is over. Then remember you have how many topics? You have 12 topics, right? 12 topics. And we have already started the second topic, that is introduction to computer. Okay. So today what we do is uh, we move on to the second topics because we will finish the legal and ethical aspect next time because it's a non-technical thing. So we want to do a little bit of technical and non-technical mixture. So today we'll do history of computing. Remember we did the introduction to computer, so that we have already done. So today we are going to do these topics, history of computer and different classifications. So we are going to do up to this point. Okay, up to this point today. So then once legal and ethical aspects are done, we have to continue with the computer architecture and different hardware parts of the computer, right? And so on. Okay. Right. So let's move on. History of computing. So the note for today's session is available in the Google Classroom. If you haven't got the Google Classroom yet, you have to send me a message if you haven't done the registration. And if you haven't got the Google Classroom invitation mail from aurora@gmail.com. So, and you haven't accepted, let me know. Okay. Right. So note for today's session is under introduction to computer, evolution of computer. So this is your note. Okay. Evolution of computer, and two quizzes are available, the easier one and difficult one. Okay. Challenging one. Right. So let's start evolution of computer. Okay. Right. So you have the PDF version, which is very compact, only related to your syllabus things are there. And I will be using the PowerPoint version of that one. Okay. And at the end, we will be able to do the quiz also, depending on the time available. Okay. Right. Right. So the first of all, why do we study the evolution of computer? For two reasons. So the first reason is, remember this is IT subject. When you are learning IT, the computer is our main tool. So when you learn history and how the computer gradually came into this shape, right? So we are in a better position to understand why the computer is like this and what is going to happen in the future, the patterns. That is the same reason why you learn history in school. So when you learn the history or the evolution of humans, how the humans have evolved to the current position and how we dominated, right? So then we are in a better position to understand who are we, right? Who are we? Why are we behaving like this? How did we get this leadership? And so on. So that is to understand ourselves. You have the history. So this is history of computing. So this is obviously humans made it, but let's see how it evolved to the current. And you know what is the modern shape of a computer, laptop, smartphones, and so on. So then you will be in a better position to understand why the modern computer is like that. That is it. Reason number one. The reason number two is, of course, we want to appreciate the great people in the history who contributed their mental, right, uh, logical thinking, engineering, right, and different contributions, right. So just like when we say science, we can remember Isaac Newton, maths, Pythagoras, right, and so on. So there are few people we want to appreciate, and we don't want to worship them, but we want to appreciate their effort and so on. Okay, so that is why we are doing this particular topic, and that is why this particular topic is in your syllabus. Okay. In the exams, very rarely they ask question, maybe just one MCQ question, but every question is your marks, right? So most of the time they ask just one MCQ or sometimes no question at all in your A-level paper on evolution of computer. Okay. Right. So I would explain you. So we want to understand the evolutionary pattern or the how the history evolved, and also we want to appreciate those scientists, engineers, philosophers who contributed to the modern computer. Okay. Right. So in order to better understand the evolution or the history of computing. So I like the word evolution rather than history, because the moment someone says history, the students start memorizing things. So evolution is something you have to understand. Okay. See the pattern. Right. So we can, for our ease of understanding, we can subdivide them into manual era, just like the human evolution, we can subdivide into hunting era, agricultural era, industrial era, and the information era. So this is evolution of the computer, the manual era, or the manual computing devices, mechanical era, the use of mechanical devices for computing. Computing means actually until very recently, until 1930s, 40s, the computing means calculating, or basically those were calculators. Now only we have the general purpose computers which does calculations, word processing, graphic processing, image, audio, video, and everything. But you will find that until around 1940s, 50s, pretty much when we say computer, it was doing like a calculator. Okay. So those are some other things you have to understand while you are learning this topic. Okay. So the second era is the mechanical era. So there we look at some mechanical computers. So then we'll move on to the electromechanical era, where the computer is powered by electricity, but processing is pretty much again still mechanical. And then we'll look at the electronic era or the modern era of computers. Okay. So manual computers, mechanical computers, electromechanical computers, and electronic computers. So that is how you subdivide the computer evolution into 4 eras. So we'll start with manual computers or the manual era. Okay. Right. So while you learn this, remember we have purpose. Our purpose is not just memorizing this and that person and this person, right? So that is waste of your time. So we want to understand how these arithmetic processing devices gradually became general purpose devices, because our modern computer is a general device. How the computer moved from analog to digital, how the computer moved from denary to binary. And you will find that early days of evolution was in Western Europe. Like we will be seeing some people from Scotland, Britain, right, England, German, France, and so on, more and more. But later on, you will find that all of a sudden, almost everything is happening in North America, right? And the reason behind that, so that is how the things are interesting, rather than just memorizing things without any context. Okay. And also the non-programmable computers gradually became programmable computers. These days, the computer can be programmable. That is why we need software developers. Okay. And also, early days of computers were just maybe one machine. Of course, the only one exception to that is the abacus, but most other machines, just the inventor use it. Just inventor you invent it and use it. It was not popularized among the others. Right? Just one of that machine was there. But now we have the commercial use, right? So we have millions and billions of computers used by from different brands and so on. Okay. So you think about those things, right? Think about those things. This is not just memorizing things. This is understanding how things gradually came into the modern shape and size. Okay. Right. So we'll start with the manual era. Right. Manual computers. Manual means not even mechanical things. Everything is done by hand. That is what is mean by manual. You know what is the difference between manual gear vehicles and auto gear. So manual means gear change has to be done manually by hand. So here also the device is there, but we have to manipulate. Manually, we have to do the calculation, but it's faster than just use our memory. Okay, so that is what is mean by manual computing devices. So there may have been so many manual devices, but we will only look at two devices because this is the ancient history. So we'll look at only two milestones in manual computing devices, that is abacus and Napier's bonds. Okay, abacus and Napier's bonds. So let's first look at what is abacus is. Okay, so abacus is something you may have heard, and it's a very popular device. But for these days, we don't use it anymore. But this used to be a popular device before, especially the modern computers came into the picture. Okay. So abacus is something like you use in your maybe you have used this in your grade 1, the calculating to help you understand addition or basically the basic understanding of a number, addition, subtraction. They use this kind of a device. Actually, this is a abacus. Of course, what you use is not abacus. Something maybe just one part of that is there just for you to play around and I understand what is counting, what is 1, 2, 3, and so on. Okay, or maybe just to understand what is addition, right? So you have 2 pebbles and 3 pebbles. Now you have 5 pebbles and so on. But if you arrange it in this kind of a format, okay, and there's a technique to do calculations, even multiplication and division very quickly. So this device had been used by people for since 2500 BC. You don't have to memorize these years. Okay, so this is for just to you to get a feeling about it. So now we are in 2023 AD. Right, so that means this is before Christ. So that means the abacus, the concept of abacus was first developed about 5,000 years ago. Right, about 4,500 years ago. Right, more than 4,500 years ago. So you can see how long ago people start looking for computing devices. Computing devices. Right, so that means we have been counting for more than 4,000 years, and the moment people start familiar with numbers, they were looking for some mechanical, some way of some devices to make their life easy. So we call it now abacus, right? Abacus. So that is, we can't say that is the first manual device, but this is the one of the documented device in the history. So therefore, we consider this as sort of the best, sort of the first manual computing device. So what you have to remember, it was capable of, or it is capable of doing basic arithmetic operations, add, subtract, multiply, and divide. Okay, add, subtract, multiply, then divide, and it's a manual device because no mechanical law, any other mechanisms were used. Just we have to manipulate it. Right. So the second device is not from far away, not right. So this is 1617. So 1617 means about, right. So now we are in 2023. Right. So about 500 years ago, right? About 500 years ago. In Sri Lankan history, this is, I think we were under Dutch control, right? We were under Dutch control. So therefore, this is not very long time ago. A mathematician called Napier, a Scottish mathematician from Scotland. So he is very famous because he is the mathematician who came up with the idea of logarithms, right? Log, something like this notation. So this particular concept was discovered or identified by Napier. And Napier, therefore, Napier was a mathematician. And you know that mathematicians are good at, or they are sort of engineers as well. So he not only came up with this idea of logarithms, right? The logarithms are super useful when you want to do multiplication, division fast. And also when you have decimal numbers and we have very big numbers. So the logarithms make your life easy. But these days logarithms are less used because we have calculators. But before calculators came, people use logarithm table to do those calculations. Okay. So therefore, logarithms help doing especially multiplication, division, finding square root, and so on, relatively easy. So the person who came up with this idea of logarithms, he built a simple arithmetic device as well, with the use of the logarithms and related concepts. And today we call that Napier's bonds, right? Napier's bonds. So it was made using ivory strips, right? Ivory strips. So that is why we call it bonds, okay? Because this is around 1617. And it has some stripes or strips, okay? So those can be manipulated, right? You can laterally manipulate them, and then you can do the by changing their positions, especially the multiplication and division can be done. Okay, so if you look at, you can see that this is 7 into 2 is 1, so that is 14. 21 written as 2 divided by 1, 28 written as 2 divided by 8, 35, 7 into 5 is 35 written as 3 divided by 5, and so on. And then you have to manipulate these things. For example, this is 400, 4, 6, 7, 8, 5, 3, 9, 9. You can see 4, 6, 7, 3, 8, 5, 3, 9, 9, and so on. So then you have to manipulate this, and then there's a specific way to find the final answer, which you can find it faster than do it manually. But again, you don't have to understand exactly how it is done. Don't worry. And there's a similar technique for the division also. But what you have to understand is not how exactly this is done. The Napier's bonds came up with a clever way of doing especially multiplication and division, and also square root faster, right? Faster. So it is a device which we can use to do multiplication, division, square root. Of course, you can do addition and subtraction as well, much faster than abacus. So therefore, it's a computing device. It's a computing device, and again, we have to do it manually. So therefore, it's a manual device. It's a manual device. Okay. So the main difference or the main enhancement is, so it has a better support for multiplication, division, and additional support for square root as well. Right. So abacus has the basic support for addition, subtraction, multiplication, division, but not for square root. But Napier's bond use a different technique, more sophisticated technique, and therefore it makes especially the multiplication, division, and square root calculation much faster, and also it support the decimal points as well. So those are the tiny things that you have to understand or remember how the things evolve, right? How the things are evolving, how the things are getting more and more sophisticated. Okay, right. So that is Napier's bonds. So that was not so long ago, about right about 400 years ago. Okay, about 400 years ago. Right. So now we are done with manual computing devices. So we just look at two milestones: abacus, which is a basic manual device which you can use at subtract, multiply, and divide. And then the Napier's bonds and special support for multiplication, division, and square root. And another thing you have to remember is it supported the decimal point. Especially, you know that decimal point play a big role when it comes to division and multiplication. Right. So now we move on to the mechanical computers. Okay, mechanical computers. So mechanical means we use mechanisms or machines. Okay, so the words that comes with mechanical is machine. So for example, so sewing machine, right? So we have machines for cutting grass. So that means it uses some mechanical things, gear wheels, right? Pistons and so on. Okay, bells, gear wheels, pistons, and so on, shafts. So then we say it's a mechanical device. So some sort of mechanism is there, right? And sometimes we can automate it using power, like steam power or petroleum power or whatever. Okay. But still no electrical power. Power can be there, but power is not given by electricity. But some now early days of mechanical computers were not powered, only the mechanism was there. Still human hands were used, but some mechanical mechanisms were used. Okay, some mechanisms were used. Right. So under mechanical era, so that you can understand obviously after 1600, because the Napier's bonds were used in 1617. So we'll look at few important computers or computing devices. We can't say computers, computing devices. What are those? Pascaline, developed by Pascal, a very famous mathematician again. You can see the mathematicians involved in these devices. Then Leibniz wheel, another mathematician who came up with the Leibniz wheel mechanical computer or mechanical calculator. Then we look at a concept called the use of punch card, which is a super important milestone in the history of computing. And then we look at the analytical engine and reference engine developed by Charles Babbage. So we call Charles Babbage, some people call him the father of computing or father of computers. And also we look at the first programmer, Ada, who wrote some algorithms to be run on the Babbage's analytical engine and difference engine. Right. So those are some of the important milestones or devices, and some of those are concepts in the mechanical era. Okay. So we look at one by one, starting with Pascaline. Okay, Pascaline. So Pascaline is an arithmetic machine. It's a machine, right? You can see all of a sudden, you can see some gear wheels and so on are there. Of course, this is what you can see outside, right? So this is a prototype made later, right? This is not the exact Pascaline, but this is something after documentation and so on. People have again redeveloped it. Okay, right. So this was developed by a French mathematician, Blaise Pascal, right? Blaise Pascal. So Pascal was a very famous, or Pascal is a very famous mathematician in history because he came up with this. There's a concept called Pascal triangle and so on. Those who are doing A-level maths, you will definitely do this part, Pascal triangle. When you expand something like a plus b to the power n, there's a nice pattern. Like remember, a plus b to the power 2 is a squared plus 2ab plus b squared, then a plus b to the power 3. And there's a nice pattern here. And these numbers have a pattern, which you can find it using the Pascal triangle. So it is this mathematician who came up with, identified that pattern. You know that mathematicians are good at understanding patterns. So they understand the pattern and just present it as a theorem or something like that. Okay. So Pascal, being a clever mathematician, French mathematician, he came up with some mathematical concepts as well. So that is a different area. We are not concentrating on his contribution of maths. Rather, what we are interested is he developed a mechanical computer, right? Mechanical computer to help his father for tax calculations, right? Help his father for his the tax calculations, and it will use some mechanical gear wheels. So that means it's no longer manual. So it uses some mechanisms to do the calculations. That is good. So that is, we are going towards automation, right? Automation. So we call that Pascaline. Pascaline, that is our first mechanical computer or the mechanical calculator. And it was able to do addition with carry. So carry means you know that 5 plus 8 is 13. We carry 1 and so on. So we'll be doing those things further when we do the representing data in the computer. Right? So it was able to do addition with carry and subtraction. Now you can see that multiplication and division is missing. Right? For example, we were able to do multiplication and division using abacus. People were able to do multiplication, division, and not only that, even square root calculation using Napier's boards. Right? But those were manual computers. Right? No mechanism was there. But this time, though the Pascaline is not used for, it is not supporting multiplication and division, still this is an advancement. This advancement, why? We are going towards automation. We mechanize things. So someone has to start it. Someone has to start it. And of course, the multiplication and division was supported indirectly. That you all know that multiplication can be done with the help of addition. Right? Division can be done with the help of subtraction. So that way it's supported, but not as a core concept of maths, multiplication and division. You know that there's a independent mechanism for multiplication and division, right? So you all know. But this use the repeated addition and repeated subtraction to do the multiplication and division. So that therefore multiplication and division is not directly supported. So that is an important missing part in Pascaline. But though those two are not supported directly, still this is an important milestone because this is the first attempt to mechanize things. Okay. So again, you can see it is not far away. 1642. Again, don't memorize the years. This is for you to get a feeling. Otherwise, you have no feeling about your subject. Right? It's dry. Right? It's dry. So then you say, I can't remember. This is boring. That means you are not part of that story. You are not part of that evolution. So you want to take up the next generation of, right? You must be the next generation of engineers, right? You must be the next generations of mathematicians, scientists. So then you want to, if you want to take their baton and run from that point onwards, first of all, you must know how the things evolve. Okay, how the things evolved, how we came into this point. Okay, so therefore Pascaline is another important uh, device because it's the first mechanical computer. Okay, first mechanical computer. So when you have free time, just take a piece of paper. Remember, studying is not reading notes. So a lot of students thinks නේ අපි පාවිච්චි කරන්නේ පාඩම් කරනවා කියලානේ. මේ කවුරු හරි ලියලා දෙන note එකක් පාඩම් කරනවා කියලා. No. Studying is you take a blank paper and you write this. right? You write abacus, what are the features of abacus, process, cons, right? So then maybe the Napier's bones, right? What are the improvements? Then you can write pro maybe into the mechanical era, Pascaline. So you can see that addition is there, subtraction is there, multiplication and division is not directly supported, but it's indirectly supported, right? So Pascal is also mathematician. So that is called mind map, right? So so a lot of students, you know that some students spend hours and hours to pass their exams, right? So ඇහුවොත් බැලුවොත් හැමතිස්සෙම පාඩම් කරනවා, ස්ටඩි කරනවා, ස්ට්‍රෙස් එකේ ඉන්නේ. හරි වෙන ජීවිතයකුත් නැහැ. But some students, they are very smart. Why? They know the art of studying, right? So when you're studying, don't just keep reading notes, right? If you just see whether you how just try to put it into a mind map and see how they are interrelated, and maybe once in a while draw a mind map and see whether you have better understood it. You can have you seen a different relationship between those things. So that is what studying is all about. Studying is not reading, memorizing someone else's note and vomiting it in the exam paper. That doesn't work. That may work for you, get good results, but definitely those kind of people, they don't contribute to the society. They don't do any serious stuff, right? They don't do any serious stuff because they have very little understanding, very little feeling about the subjects, what you are learning. So these guys are just learning for the sake of learning, passing exams, getting certificates, right? And they plan to do nothing. So they plan to do nothing, right? Right. So therefore, Pascaline is the first mechanical computer developed by French mathematician Pascal. He used to use it to help his father to do the tax calculation, and Pascaline was able to do addition and multiplication, addition and subtraction. The multiplication and division was only indirectly supported using repetitive addition and repetitive subtraction. Okay, right. So now we move on to our second mechanical computing device. Look at the years again, not to memorize, just to see the context. This is 1642, French mathematician. So the next one is 1673, German scientists. So you know that France and Germany are the neighboring countries, right? Two neighboring countries. So Leibniz, the German scientist Leibniz, came up with another mechanical device, a mechanical computing device. We call this Leibniz wheel because it uses a wheel. Because it uses a wheel, we call it a Leibniz wheel, not just one wheel, set of wheels. And sometimes we call it step reckoner. So this is another name we use. So either you can call it Leibniz wheel because Leibniz is the person who developed it, or you can say step reckoner. So this was developed few years of about 10-20 years after Pascaline was developed by Pascal. And this was made by using a cylinder with set of teeth. Teeth can cut. Teeth can cut. So if you do a Google search, you can find a bit. You can see so something like this. So you can see there are teeth there at different varying length, and this is connected to a gear wheel, right? Gear wheel, and these are in the various lengths and size as well. So that concept was used by Leibniz, especially to do the multiplication and division faster. Now remember, one of the missing point or weak point of Pascaline was the multiplication and division was not directly supported. But when it comes to Leibniz wheel, it was a mechanical device. Now you can clearly see that it's more sophisticated device than the Pascaline, obviously. That is why that is how the evolution goes, right? You make more and more things right? You make it more and more sophisticated. So using the Leibniz wheel, we can do the multiplication and division much straightforward way, not indirectly by repeated addition and repeated subtraction. So therefore, this is definitely an enhancement, improvement of the Pascalite. And also we got the multiplication and division and also square root back into the calculations. But now these are mechanical computers. Those are done using mechanisms rather than hand manipulation by humans. Okay. So that is Leibniz wheel or step reckoner. Now we have discussed how many? We discussed abacus, a manual computer, then Napier's bonds, another manual computing device. So then we moved on to French mathematician Pascal's Pascaline, which is capable of doing addition and subtraction, but only indirectly supported multiplication and division. And then the Leibniz wheel or the step reckoner, which use a cylinder with set of teeth with incremental lengths and coupled with counting wheel. So this is the counting wheel basically, which supported multiplication, division, addition to the add and subtraction, and also the square root calculations. Okay, right. So that is improvement, definite improvement, and also now we are in the mechanical era. So our next, it's not a device actually. Next one, it's a very, very important concept. Right? One of the most important concept in computing, the concept of punch cards. Right? Concept of punch cards. And this is 1800. 1800 means in Sri Lankan history. So that is only about, now we are in 2023. So we are talking about 200 years ago. 200 years ago, 200, yeah, 200 years ago. So this is again a French inventor, Joseph Jacquard, a very famous person in the history of computing, Jacquard's punch cards. So Jacquard came up with the idea of program. So this is the inception of program. Now we have the concept called program. Right? You have topic called programming using Python programming language. Okay, and so on. So we have programming languages like Java, C, Python, C Sharp, and so on. So this is where the concept of program came. Now remember, when it comes to the earlier devices, there was nothing called program. It was, now for example, Leibniz wheel, these levers are used. So we have to still manipulate. Only thing is some mechanisms are used. So we do one calculation by manipulating these levers and so on. So then we can get the answer by looking at these values in the wheels. And then we have to do the next calculation. Only thing is we use mechanisms, but there's no program. So program, or the user, operator must know how to operate it. And every time the operator has to operate it and get the result. Of course, it's something like the bus ticket machine. Of course, bus ticket machine is not a computing device, but so the operator has to operate it by adjusting certain things. Now, every time the operator has to do that. There's no program. Okay. So then came this idea of program. Right? Program, because someone has to think about it. Now, what is the advantage of program? Can someone tell me? Because we have a topic called programming also later. Why is it important, or what is the advantage of having a concept called program? Anyone? Just I need your gut feeling. So there's no technical answer. Of course, I'm not talking about the program in a particular, say, for example, when we have function also, we have right agenda or program. I'm not talking about that kind of thing, right? But we have programs in software. or computers, right? We install, so when we say software, basically software is a program. Software is a program. So my question is, what is the advantage of having a program or writing a program? Anyone?
We can give a set of instructions to the computer.
So we can give set of instructions manually also, right? So for example, here also we are giving instruction by, right? For example, say you are turning on a rice cooker, oh, so sorry, the gas cooker. That is also giving an instruction, right? So what is the advantage of writing a program? Oh, my question is, what is the advantage of giving those instructions in the form of a program rather than we go and do things?
So then always we do not want to give the instructions.
Yeah,
It
that
is
is
stored.
yeah. So that is the perfect answer. So once you write the program, right? So the program is already there. So you don't have to go and do this and that and other things all the time. So you write the program only once and then let the machine execute it. Let the machine execute it independently or with minimum interaction from our side, right? With minimum interaction from our side. So otherwise, we must be there. Now, very good example is actually this was first used in weaving machines. Weaving machines. So machines people used to weave fabric, right? To weave fabric. So if you have seen in Sri Lanka also, I think these days we don't use it anymore. Maybe still some people use it. There's something called hand looms. Okay. So if you go to the YouTube, still you might be able to find some way. I think even Sri Lanka still some people use it. Right? Say hand loom machine. You may have seen this. Something like this.
Lakshmi is now giving us the demonstration.
So you can see that. So this person has to manually do it, and it's even more difficult in some cases. So in countries like Sri Lanka, so the person has to remember the pattern. That is the most difficult thing. The operator has to remember the pattern because the program is in his or her mind. Okay, in his or her mind. Right. So this is, I think, Sri Lankan version. See, it's not an easy task. So these people can weave different fabrics with different patterns, but that pattern must be remembered by the person. So, and also that person must be there all the time. And think of a person who spent 8 hours for weaving, right? So that person is super tired, right? Super tired. So what Joseph Jacquard, this French inventor, thought is this is doing boring tasks, right? With human effort, right? Human effort. So that is not productive and it's very stressful for these people, operators. Okay. So what he came up with is this idea. Okay. So you can see 2000 years old Jacquard loom technology. So what he thought is, why can't we write it into a program?
First, the fabric design is translated to graph.
Okay.
These are
I will share this in the WhatsApp group also for the time being, because you can just have a look at these things, because otherwise you don't get a feeling about what is the importance of these inventions, right? So now what Jacquard did was he took that pattern into a punch card. Punch card means it's a card. You can see this a card and there are punch. right? Set of punch, and it's a continuous card. Actually, one card, second card, third card, and so on. And each one has different punch. And the machine has hooks, the metal hooks, and the hooks will fit onto these punch. If the punch is there, it will fit on. Otherwise, it is not fitting to that. Okay, so let me show you.
For
You can
pattern
see?
and allows the hooks to pass.
So whether it's hooked into the punch or not determines the pattern. Now, what is the advantage? So there are two advantages. One advantage is now that human operator who worked tirelessly hours and hours, right, doing different manipulation is no longer needed. So which is good, right? Which is good. Right? So that human operator doesn't need to do that kind of complex manipulations. Okay. Now, can you think of the second usage? Now, just that guy has to do a very simple thing. Of course, at that time, now of course, that is also we use electrical energy and so on. But at that time, there was no electric power. That is one usage, one advantage. The human user's mental, very stressful task work is not needed all the time. What is the second advantage? Can someone tell me the second advantage? Just think of it. Just think of it. So remember now the pattern is in the punch cards. The patterns are in the punch card. Okay. So what happens? What happens if we want to change the pattern? Now say next day I want to weave a different pattern. Or we have say 10 patterns. We have fabrics of 10 patterns. So now we don't need 10 machines or 10 different people or people with 10 different skills or one person doing different patterns and each day. Rather, we have 10 different set of punch cards. So this set of punch card is for pattern 1. This set of punch cards are for the pattern 2. Now, second day, if you want a different pattern of fabric to weave, we just change the punch card. We just replace the old punch card with the new punch card, other punch card. So this is your program 1. This is your program 2 and so on. So now we do the same thing. Of course, when we want to do word processing, we have the MS Word. When we want to do some calculation, MS Excel, different pattern, different program. When I want to do some chatting, I have the WhatsApp. When I want to do some graphic editing, I have the Photoshop. So one machine, different programs. One machine, different programs, rather than having different machines. So we don't need word processing computer, graphic processing computer, or I don't need a separate word computer and so on. So we have one computer, different programs. So who came up with this idea? So it is punch card. But only thing is punch card is not a software. Punch card is also hard because it's a sort of a cardboard with punch. But this is the program. So this is the inception of the concept of program. So therefore this is super important milestone in the history of computing. Super important milestone in the history of computing. Okay, so this was developed by Joseph Jacquard, a French inventor, and this was first used in weaving machines, right? Weaving machines. Okay. So then someone will ask, how does it related to computing? Because this is a weaving machine, but this is the concept of program. So concept of program. And also you can see that this is a binary program. Why? So it has some rows, it has punch, some other rows, maybe it has different punch at different places. So punch means whether you have a punch or whether you don't have a punch. So maybe have a punch, we can call 1. Not having a punch in a particular location, we can call it 0. So you can see that this is a binary program, right? Binary program. So 1-0 level program. And you can see sometimes you might be wonder why computers are using binary numbers. Why computers are binary, right? So when we are familiar with denary numbers, so base 10 numbers, right? So why computer engineers or engineers use binary numbers to develop computers? So this is the starting point of the program. You can see that the very first program was also binary. The reason is keeping two state is easier than keeping multiple states. So can you think of keeping 10 different states in a punch card or simple mechanism? Right. So that mechanism is going to be more complex because we have to differentiate 1 from 2, 2 from 3, 3 from 4, right? And so on. But this is super easy. Just we have 1 and 0. Whether we have punch, if we have punch, the hook will fit into that. If you don't have punch, the hook will just float around it. It is not fit into that, right? So that is the concept of binary program, or basically the concept of program. Okay. Though it was not used for computing. So this is the concept that later computer engineers, right, mathematicians use to feed the programs to computers, right, to the computer. So this is the inception of the idea of program, which is super important, a clever idea, right, clever idea, right. So that is Joseph Jacquard's punch card. Okay, so now we have discussed 3 things. Pascaline, right? So then we discuss the Leibniz wheel, and then we discuss the concept of punch card. So again, punch card is under mechanical computing because these punch cards were used in mechanical devices, right? The weaving machine was a mechanical device which will either pick the punch or not pick the punch using those hooks. Okay. Right. So now we move on to our 4th milestone in the mechanical computing. So this is the most important thing. That is why I told you the Charles Babbage is called the father of computing. Remember, the punch cards were used in weaving machines, not for calculators, so the computing devices. So Charles Babbage, so this is 1880 in Sri Lankan history, right? So remember 1815, even the Kandy, the central province was also under British rule. So that means we were under full British rule, right? While we were under the British rule, so this is another British English mathematician and scientist. So he developed what is known as the first computer. Okay, first computer. It's a mechanical computer. Charles Babbage came up with 2 devices. The first one is called analytical engine. The second one is called difference engine, right? Analytical engine and difference engine. So why do we call Charles Babbage the father of computing? So this is the first serious effort of developing a general purpose computer. Because so far it was just some arithmetic machines, okay, doing certain arithmetic calculations. But this was again arithmetic and algebraic function, solving arithmetic and algebraic functions. But this has the all the features of a modern computer. So set of input devices, set of output devices, the control device, processing device, storage, temporary storage, we call them registries now. So all those features were there inside this machine. Oh, those two set of machines. Actually, he developed two machines. So the first one is called analytical engine. The second one is called difference engine. And not only that, he automate the process by using steam power. Right? You know that even in Sri Lanka, when the first came the trains and so on, even the cars and so on, so they were powered by steam. So then only came the hydrocarbons like petrol, diesel. This is 1880. So at that time, so he managed to power it using steam power also. So therefore, this is a serious effort to make a computing device. Okay, but due to the limitations of technology at that time, right? Due to the limitation of technology at that time, these machines were never fully functioning, right? Fully functioning, but still, this is the first serious idea of a general purpose computer. So therefore, we still, though those two devices were not 100% functioning, we still call this Charles Babbage as father of computing. So what are the things you have to remember, right, about the Charles Babbage? So we call him the father of computing. So he came up with two devices, analytical engine and difference engine. And it had all the component of a modern computer, okay, modern computer. And also it used punch card for input programs. So now you can see he's using the punch cards for the computing purpose, not for the viewing. And also it was steam powered, right? Steam powered. Okay. Right. So that is a very important milestone. So no wonder why we call him the father of computing. Okay. Right. So the next important thing is, right, I told you that it had the input, output, control, and so on. Okay. So this is sort of a later on, the museums have developed a prototype of one of his device, right? So this you can go to this link. Okay.
That is the first successful transference of intelligence to machine.
All mechanical, designed by British mathematician Charles Babbage in 1822, but never built.
It's famous for two things. It's famous for inventing computers and for failing to build them.
So Doran Swade persuaded the Museum of Science in London to build what Babbage only drew, eventually making two, this one on display in Silicon Valley's Computer History Museum.
Babbage's time, there was no standardization. So you could not make a nut in Manchester and a bolt in London and expect it to fit.
It's called a difference engine because it doesn't multiply, it only adds. That doesn't make it a glorified abacus.
No.
It solves complex polynomial equations like this one more precisely than any handheld calculator. Set the initial values, clear the memory.
Right. So I highly encourage you to go through this video. Okay, go through this video, right? Not to memorize things, but you must get a feeling about it, right? Get a feeling about it. Otherwise, what happens is you don't have any, right, real feeling about these inventions and so on. You just hypothetically, right, imaginarily be memorizing these things, right? So if you try to memorize something that you have no feeling, you understand, no idea, so that is where the education really failed, right? So therefore, I highly, after the class, I think this is about 5 minutes video. So go to the YouTube link and make sure you look at it. Have a look at this one and also have a look at the punch card, the concept of punch card. Okay, so then it will never ever forgotten because you have a real feeling about you become a part of that history, right? You have witnessed the history. So that is why you have the advantage, right? You have the multimedia, you have the internet, you have the YouTube, right? So those who are not using those things, they are just working with papers, printed books, right? So their world is very narrow, right? Because they live in 1980s and studied ICT in 2023. So don't get into that trap. So you are living in 2023. Use all those resources and take that leadership. Take the leadership or take the lead and go very fast. Okay. Right. So just have a look at it. Right. Maybe just once, or if you are interested, maybe once or twice. I don't mind. Right. So that is Charles Babbage's analytical engine and difference. Of course, Charles Babbage never made this kind of a sophisticated engine. This is something that they have recreated using the idea of now. In the video, they explain these cams are right working as a control unit. So in the microprocessor, we have the control unit and ALU. So this is the controlling unit, of course, the mechanical controlling unit. So later, computer engineers managed to make it to electronic controlling unit. Okay, right. Right. So the next important milestone is tightly related to Babbage's difference engine and analytical engine. So that is Ada Lovelace-King. Ada King, another English mathematician. Actually, she helped Babbage by writing some algorithms. So therefore, basically, Babbage, then Ada, and also how do you call that person who came up with this punch card? Yeah, Jacquard. So they work, collaborate, right? Babbage, Jacquard, Ada. Of course, Babbage and Ada both from UK. Jacquard is from, I think, France, right? France, yes. So they collaboratively work on that. So basically, especially the Babbage and Ada collaborated because Ada wrote the algorithms to be run on the Babbage's machine or Babbage's computing devices. Okay, so remember those devices use punch card. So those punch card needed the programs. So Ada wrote those algorithms to be run on these devices, but unfortunately these devices were not fully functioning. So therefore these method calculations were not 100% done, but still we consider Ada as the first programmer. And you can see that the world's first programmer is not a male, female. So no wonder we call this software. So they involved in soft side more and more, like programming, because you know that when it comes to physical things, right? Physical things, the male, right? The man has advantage. So their strength is higher, right? Strength is higher. But that is physical. So that is why when you go to even Olympic, there's a men's 100, women's 100, women's 100. Right? But when it comes to mental capacity, so you can't say one is better than the other, right? So you can see that. So Ada is writing the programs and Babbage was developing the hardware. Okay, Babbage was developing the hardware. So that is another important person, or not that, she is another important person in the history. That is Ada Lovelace-King, the programmer who wrote some algorithms to be run on analytical and difference engines. Okay. Right. So that's the mechanical era. So some other people had also developed some devices, because we can't discuss all the devices people made. Just we picked some important, more prominent devices only. Okay. So any questions up to this point? Because we have come up to this point. So starting with manual computers or manual computing mechanisms like abacus, to the modern mechanical computer, difference engine and analytical engine. Okay. Right. So now, if you don't have any question, we'll move on to the electromechanical era. Okay. electromechanical era. So why do we call it electromechanical? Remember the earlier one, those were mechanical. The only thing is now we are using, or in the electromechanical era, people use electricity to power. Remember the difference engine and analytical engine use steam power. That is 1800s. Okay. Now we are into the 1900s. 1900s or latter part of 1800. That is the time where the electricity was invented. And this is a very important milestone. And you will find that up to this point, we were talking about British mathematicians, French inventors, German scientists, and so on. You can see it was pretty much Western Europe. German, British, Scottish, right? French people involved in these inventions or the evolution of these computing devices. Of course, the abacus, we can't say it's a European, but from that point onwards, from Napier's bones onwards, right? Pascaline and so on, it was pretty much Western Europe, right? Western Europe. But you will find that when it comes to electromechanical era, it is mainly USA or America, right? USA or America. So there are two main reasons. There are two main reasons. Of course, still the British, French, German people are contributing, but they are playing a secondary role, and the main inventions are coming from USA. So this is part of you understanding the evolution. So can someone tell me why? Use your common sense, use your knowledge about the world history. Now remember, now we are into 1900s. Now from Western Europe, the focus is more in the America. And even today, when we say computers, right? Apple, HP, Dell, Intel, AMD. So it's all American. When it comes software, Oracle, Microsoft, right? Social media and so on, Google, Facebook. So they are all American. So even today, the dominance, almost all the big names are, right? Maybe 95% out of 100, they are from USA. So that leadership took in early part of 1900. And we know that America is the superpower. Why they got that superpower? One reason is they got that lead in IT, computing, right? So can someone tell me a possible reason why the American people go past the Western European people? So there are two main reasons. One reason is obviously in America also it is the French, British, German people. So they colonize. So remember the America was colonized by British, German, French people. So therefore it's the same set of knowledge. They took the other main reason was it was during the 1900s to 1950 there was World War One and World War Two. So the World War One and World War Two was in Europe. So they were busy fighting with each other, right? Fighting with each other. But any of those wars directly affected USA. So that was another reason. So therefore, America had the peace, relative peace, or very peaceful, because they never involved in any of those wars. Of course, they involved in the World War II at the very last moment, right? And they just finish it also. Okay. So therefore, that is why they took the leadership. And when it comes to especially electricity, the American engineers, scientists took the leadership, like Faraday, Thomas Alva Edison, Tesla, then other people like the mechanical side, diesel engine. So those were all American people, right? So then, of course, the Wright brothers, the plane, Marconi, radio, right? John Logie Baird, television. So they were all American. So the reason was it was the same thinking, same talent, as well as they had the peace. And therefore, the IT field also, the evolution of computer also predominantly happened or transferred to the UK, sorry, to the America. Okay, right. So let's move on to the electromechanical era. Right. So obviously it used electrical power and continued to use the punch cards because these are not electronics. So still we are in the electromechanical era. And of course, the more influence are coming from USA. Okay, coming from the USA. And still, even today, when someone is doing ICT, you know that. So the influence or the major influence, your computer, microprocessor, your Windows operating system, or if you are using Apple or Mac, if you're a smartphone user, your Android operating system, everything is USA. Of course, the Chinese people build it, but the architecture and everything is USA. And that is why they are now taking the Chinese manufacturing process to India and other countries because there are some political issues. Okay. But the China, they don't manufacture microprocessors. So they don't have the knowledge to build a operating system. So they don't have databases. So they just manufacturing things. Okay. They just manufacturing things for these big companies in the West. Right. So now let's move on to the electromechanical era. So we'll look at 4 main milestones. Okay, so tabulating machine by Hermann Holrich, the concept of universal machine by Alan Turing, the Z3 and Z4 computers, and Harvard Mark series. Right, Harvard Mark. So Harvard is, you know, a famous university in USA, Harvard University. So they are also involved in this Harvard Mark series. And the Harvard Mark computer started as we have Harvard Mark 1, Harvard Mark 2, and so on. So the first computers were electromechanical, the last computers were electronic. So therefore, Harvard Mark is a part of the transition from electrical computers to electronic computers. So that is why Harvard Mark computers are super important in when you are learning the history of computing. Okay. Right. So let's look at the tabulating machine. This is 1890. Right. So very close to the 20th century. Okay. Right. So this was the first electromechanical computer. Right. What is the first electromechanical computer? Tabulating machine developed by American inventor Hermann Holrich. So Hermann Holrich is another very famous person in the history of computing because he is the one who later formed the IBM company. Of course, these days IBM is not a big company, but until around 1980s, when someone says computer, because in 1980s there were no Apple computers or Dell or whatever. So if someone says computer at that time, everyone is talking about IBM computers. So you can see that it all started in 1890. It took about 19 years of dominance. 19 years of dominance was by IBM company. It all started in 1890. So Hermann Holrich developed, we call it now tabulating machine. A tabulating machine, which was used to process census data of USA. Census data, සංගණන කරපු data. USA වල සංගණනයක්. So, and of course it used electricity. So that is a milestone. because that was the first serious computing device that used electricity for power. And also it continues with the punch cards. Okay, punch cards. So therefore it's a electromechanical computer. Electromechanical. Processed mechanically but powered by electricity. And later he founded the IBM company. And in the electronic era, early days, IBM computers play a key role in mainframe computers, mini computers, and later on the IBM microcomputers, so the PCs. Okay, right. So that is tabulating machine by Herman Hollerith. So next we look at another concept. Now remember, this tabulating machine was built for one purpose, that is to do the census related calculation. Still the computers were focusing on one task. Of course, the programs are there, but pretty much the programs were used to input data. Oh, it's one type of task. It's one type of tasks are done by one computer. So then came this idea of universal machine. In 1936, an English mathematician, Alan Turing, another very famous person in the history of computing. So he came up with the idea. He never came up with the computer. He thought, or he came up with the idea, why do we build machines or computers, one machine doing one task, another machine is doing another task, and so on. So can't we just build one machine which is capable of doing all the things that we do? If our brain can do different kind, we can recognize characters, we can recognize audio, video, we can do arithmetic. So one brain, right? One brain. So we don't have different people doing different things. So then he thought, or he came up with the idea, why can't we build one machine which is capable of whatever the computable, right? Whatever computable. So a machine that has a solution to all problems that is computable. If something is computable, right? Computable means we can put it into quantities, because computable means quantities, numbers. If you can put it into numbers, that computer must be able to do that processing. So right now, that is what our computers are doing. Right? So our modern computers can do obviously arithmetic. Of course, that is numbers itself. It can do word processing. Of course, our characters are given numbers, ASCII character, ASCII codes, Unicode. So, right. So then we can do it. Now you can see I can use different colors. Draw here. So these colors are also numbers. The amount of red, 0 to 255, green, another value, right? RGB values. So if something can be computable or converted to quantities, it must be processed by your computer. So that is the idea. So that is the concept of universal machine. One machine doing all those things. And that is why we have just one computer, right? We don't have word processor computer at home, image processing computer, no, right? So we have, yes, radio, television, washing machine, and blah, blah, blah. But we have just one computer. And now that computer has become your smartphone as well. Of course, if you want to take somewhere, you do it using your smartphone. But when you are at home or office where you don't have to move, you use your laptop or laptop or your desktop. But theoretically, your smartphone and desktop is the same. Only thing is, because smartphone has a very small screen, we don't use that for doing very serious stuff. Right? Business and other serious stuff, academic activities, we use the computer, laptop or desktop because we have bigger screen. But other than the screen size, your smartphone is also computer, right? Your laptop, desktop is also computer. Okay. So therefore, basically, those are all universal machines. So who came up with this idea? This idea was from Alan Turing. Alan Turing. So therefore, Alan Turing came up with this idea of why don't we build one machine or one type of device which is capable of doing all those things rather than everyone concentrate on different machines. And that is a very important concept. And not only that, he even came up with the idea of AI and so on. So why can't we make computers learn things rather than we write the programs? Okay. And so on. So therefore, Alan Turing is another important person in the history of computing. Right. So now how many milestones we have gone through? So much. Right. So now the next milestone is, now remember, Alan Turing came up with the idea. Right? Idea, not how to do it. He told this is the way to do it. Or this, we must concentrate on this way, but not how to do it. He never came up with the idea of how to build that general purpose computer. So then came the von Neumann. Right? Von Neumann. So von Neumann came up with the modern computer architecture, or we call it the stored program computer. Right? Von Neumann came up with the stored program computer architecture. So remember last time, not last week, a week before, we discussed input devices, output devices, the processor, storage, secondary storage, tertiary storage, and these are interconnected. These are interconnected, and this is called the modern architecture. And we call this the von Neumann architecture, or the stored program architecture. Our programs are loaded to the memory, and from memory it is sent to the processor and executed. So this concept is called stored program computer concept. Okay. So different programs are loaded to the processor memory and then executed at different time. And right now, of course, even at the same time, different programs can be executed as well. But it all started as let's load different programs to the memory at different times and execute. Maybe one program is doing word processing, another program is doing calculation, another program is doing image processing, and so on. So this was made possible with the von Neumann architecture. So von Neumann is the one who came up with the idea of memory. Right? Memory. And then came an alternative architecture for that called Harvard architecture. So remember we talk about the Harvard Mark series. Right? So von Neumann came up with this idea of stored programs or memory. Harvard architecture modified or refined that concept further to shape up the modern computer. Right. So those are the important milestones in the electromechanical era. Okay, electromechanical era. So stored program architecture, or the von Neumann architecture is you load your programs and data to the memory. Right. You load your programs and data to the memory and then execute it by the processor. So that is called von Neumann architecture. So that is where the concept of memory came. Now we have computers have RAM. Now we call it RAM, but at that time they just call it memory. Okay. So then Harvard architecture, so they further refine it. They thought we want to separate the program and data in the same memory, but we want to have a separate area for keeping the programs and a separate area to keep the data. So later when we look at the computer architecture, you will learn that in the computer memory, even today, modern computers, it's just same RAM, same hardware, but some range of memory addresses are allocated for programs. Different memory address ranges are allocated to data. So that means we don't mix data and program in the memory. We separate it. We separate one set of memory locations for programs and another set of memory locations are used for data. So that concept came from the Harvard architecture. So basically, Harvard architecture is a refinement of von Neumann architecture. Okay. Right. So under electromechanical era, what we have covered so far, the tabulating machine by Hermann Holrich. It was used in US census data processing, and later he developed the IBM company. Then the concept of universal machine by Alan Turing. So if something is computable, it must be processed by that particular universal machine. And then the the von Neumann architecture, where the programs and data is loaded to the memory and then sent to the processing, and refinement of von Neumann architecture, that is, your programs and data must be reside in two different areas of your memory and then loaded. Okay. Right. So using this modern architecture or the stored program architecture, now the electromechanical computers started to evolve. That means they are more concentrating on general purpose computers rather than just building a computer for one task. Okay. So the first such kind of a programmable, right, digital electromechanical computer was Seus computers. So Seus 3 and Seus 4 computers. So those computers were developed by German engineer Seus. Okay, Seus. Now you can see it's not 100% USA. Some inventions are coming from Europe also, right? So for example, the Seus computer, the Seus 3 and Seus 4 was, they use those mainly for the war-related purposes like encryption, decryption, and so on, secret messaging, and so on. And it was electromechanical computer, right? So therefore, if someone talk about Seus computers, right? So remember, the first electromechanical computer was Hermann Holrich tabulating machine. So now we have the Seus computers, also electromechanical computers, but things are getting more programmable, general purpose now. Okay, programmable and general purpose, because now they are using the von Neumann architecture, Harvard architecture, and so on. Right. So as I told you, especially using the Harvard architecture, where data and programs are separated in the memory, so they start building their own computers in USA. So Seus computers were developed in German, whereas Harvard Mark computer series, they came into the picture from the USA, and it was not owned by just one company. It was with the collaboration of IBM, Harvard University, and some other inventors. So they collaboratively came up with these Harvard Mark computers. Actually, it was started with Harvard Mark 1, Harvard Mark 2, Harvard Mark 3, 4, and so on. And when it comes to Harvard Mark 4 computer, it was an electronic computer. So remember, we were talking about the electrical computers, right? Yes, Harvard Mark 1, 2, 3, electrical computers, right? So they try to build general purpose electromechanical computers. But when it comes to Harvard Mark 4, they start using electronic, right? So that means we are moving from electromechanical to electronic. So I told you the difference between electrical and electronic, right? Electrical means we use electricity to power, right? We use electricity to power. But when it comes to electronic, the computer or that device either generate signals or consume signals or process signals. So that means now when it comes to Harvard Mark 4, it uses signals, not just to power, but these signals carry data. The signal has a meaning. Signal has a meaning. So that is what electronic is all about. Right? For example, if you take your radio, what you get is a signal, and it has a meaning. So it can be converted to sound. TV, so what you get is signal, but it can be converted to pictures. And what you get into your computer is signals, which is converted to text, audio, video, image. So therefore, Harvard Mark IV, you can see that it's converted from electrical to electronic. So that means in the background, the people, engineers, scientists develop the electronic devices. Electronic devices. Remember, the light bulb is an electrical device. But if you take radio, television, those were electronic devices. And parallelly, computer also became electronic device. That is what happened. Okay. So therefore, now we are in the electronic era. So remember, we started with very humble abacus, right? Abacus. And then we moved on to, now let's refresh it again. So we started with abacus, then Napier's bonds, which has more sophistication for multiplication and division and square root. So then we moved on to the mechanical era with the Pascaline. The Pascaline was doing only addition and subtraction, but mechanical. So then the Leibniz wheels at the multiplication, division, and square root features again, right? Mechanically. So then we discuss the importance of importance of the punch card, Joseph Jacquard, but it was used for weaving machine rather than computing. So then we discuss the analytical engine and difference engine by Charles Babbage, so which had all the components of a modern computer, but it was mechanical. So then Ada King, or Ada Lovelace King, who wrote some algorithms, right? So then we start discussing about the electromechanical era with tabulating machine from Herman Holrich, who later founded the IBM company. So then we look at, now when you look at the big picture, so that is what you have to do, right? Don't afraid to look at the big picture, like a film. So then came the concept of universal machine by Alan Turing, and the architecture. Now we have to relate one with the other. So Alan Turing came up with the concept, right? Concept. So then the von Neumann architecture and the Harvard architecture to make that a success, especially the emphasis on memory. So then what are the differences between von Neumann architecture and Harvard architecture? In von Neumann architecture, the programs and data were not separated in the memory. Harvard architecture make it separated. That means you don't have two different memory, right? For example, in your computer, what you have is RAM. But your operating system keep your programs in one set of areas, memory addresses, and data in another set of memory addresses, which make it easier to manipulate and also security and so on. And then we discuss the Zeus computers, Z3 and Z4, the electromechanical computers. And then the Harvard Mark series from USA. Just you have to remember that Zeus computers are from Germany, Harvard Mark computer series coming from USA. And And Howard Mark IV computer was an electronic computer. That means we shifted from electromechanical to electronic. Right? Electromechanical to electronic. Right. So now you must understand what is electronic and what kind of electronic devices are used and how those electronic devices evolved over the time. Okay. Right. So to better understand the electronic computers, we can separate them into generations. So we call them the first generation computers, second generation computers, third generation computers, and fourth generation computers. So don't confuse this with the processor generations. Now, when you buy a computer, right, so you know that you look at whether it's i1 or i2 or i3, i4, i5, i6, i7, and so on. And also there's a concept called processor generation. Is it 11th, 10th generation processor, 11th generation processor, 12th generation processor? So that is that is a completely different concept managed by Intel and so on. So this is not that kind of processor generations. Okay, so that is for modern computers. We have, for example, someone will say, I have i7 processor, Intel processor, and it is 12th generation. So that is a different thing. So what we look at here is very basic, right? It's more commercial thing. So this is more academic separation to understand the different mechanisms of electronic computers. So we can call them first generation electronic computers, second generation electronic computers, third generation electronic computers, and fourth generation electronic computers. So how do you differentiate? It's super easy. Right? You just have to concentrate on the processing device. Don't think about the other things. Okay, but I have added few more information, but you have to just look at the processing device. In first generation electronic computers, the processing device or the logic gate was built using vacuum tubes. That is the one you have to remember. Okay, vacuum tube. I will show you the next also. Second generation computers, it was transistor. Third generation computers, it is IC or integrated circuit. And modern computers are fourth generation, and that is where we have the microprocessor. Right now you can see how it evolved. So additional details are just for you to get the big picture, but for the exams and other things. So first generation, vacuum tubes, second generation, transistors, third generation, ICs, fourth generation, microprocessor. Okay, so that is how it evolved. Right. Because the processing device is the most important device, the processing device. Okay. Because that is what makes the computer super useful by doing the processing. Right. So just like when it comes to education, the most important thing you're understanding, not memorizing. So who cares your memory? Right? No one cares. Maybe for your exam purposes, it is good. But when it comes to a job or something, everyone is looking at your talent. Can you do something? What are your competencies? Right? They don't ask what you remember. What they ask is what kind of things you do. You can say, okay, I can develop software. I can do data mining. Right? I can build a business. So that is what everyone is interested. Okay. I can solve problems. I can come up with a new vaccine. So that is what people are looking for. Right? So if you want to migrate to some other country, they will check whether Is there a scientist in you? Is there an engineer within you? Is there a businessman in you? Right? Not you remember this and that and other things. Okay, your capabilities they are looking at, not your memory. Right. So therefore, first generation vacuum tubes, transistor, IC, microprocessor. Okay, but we'll look at few more things as well. But that is what your big picture. In first generation computers or electronic computers, that is about 1940s and 50s. Right. So this is the time where the World War is coming to an end. Actually, it came to an end in something 1940s. Okay. So they developed vacuum tube based computers. Remember the Harvard Mark IV was a vacuum tube based computer. That is why we say it's an electronic computer. So the advantage is now the processing is also done at electrical level. Or part of the processing at least is transferred to electrical signals or electronic signals. Now we are getting out of mechanical part. Now you know that when it comes to your computer or laptop, there's hardly any mechanical part. So the only final mechanical part is your fan. But fan is not doing any data processing. Fan is doing the cooling. Right? So that is your last mechanical part. Your hard disk had little bit of mechanical things, like that is why you can hear some noises, right? But that is to access the relevant portion of the hard disk. But now hard disk is also sort of a outdated thing. So now we use SSD. Now that mechanical part is also no longer there. So therefore, these days, the only mechanical part is fan, right? Major mechanical part. And so I have been using about 3 to 4 laptops. Almost every laptop, the trouble is from the fan. So other devices are perfect. You can see the mechanical things are very terrible in a way, maintenance and so on, because they get into the wear and tear also, and also they are very slow and so on. So therefore, we have now get out of the mechanical side, and we are now in sort of 100% electronic. But it all started with first generation of computers. They use vacuum tubes for the processing. Okay, so we'll cover the first generation, second generation, third generation, and fourth generation, and little bit of classification of computers next time, because we covered a lot of things today, right? Because we covered a lot of things that you have to remember also. So therefore, I don't want to finish it today itself, right? So we'll finish this topic next time. It will take another half an hour. So then next week we will finish the ICT topic. That is, remember we discussed the social and economical impact of ICT. How the ICT impact tourism, journalism, agriculture, and so on. And also we discussed the social effects. Some people get the benefit of ICT, some people get the negative things. They hate ICT. Some people love ICT, some people hate ICT. And there are some people who don't know how to use ICT. Some people, they don't have money to use ICT. Some people don't have the access to ICT. And those social issues also we discussed. But we didn't discuss the ethical and legal aspects. So how people can use ICT in a good way, bad way. So what are the illegal things? What are the unethical things? So those things we'll cover next time. So that we want to finish your topic 1 next time, and we want to do some quizzes there. And then only we continue with the topic 2. And while we continue with the topic 2, I want to start topic 4 parallelly, that is logic processing, because we need bit of logic processing knowledge to do the topic 2 computer architecture. So you can't understand the computer architecture without fully understanding how the logic gates work. And that I need in this topic also, because for example, first generation we use vacuum tube based logic gates, second generation we use transistor based logic gates. So you have to understand what is a logic gate is first. And without understanding a logic gate, you will not understand or appreciate the difference between first generation electronic computers and second generation and so on. Okay. So therefore, these topics are interrelated. So therefore, while we are in one topic, sometimes we start another topic and wait there to finish our previous topics and come back. Okay. Right. So we stop at this point. So next time we will finish this topic, evolution, because evolution is needed to get you the feeling of the subject. Then we'll move on to the topic 1 and finish it. That is ethical and legal aspects. Okay. So then topic 1 is over. Topic 2 is maybe 10 to 15% over. And while we are doing the second topic, we will move on to the fourth topic and just start the fourth topic, that is logic. And then we'll come back to the architecture and finish it. Okay. Right. So, right, we'll stop at this point. Today we'll stop a little bit early. Okay. Right. We'll stop at this point.